Well, hello and welcome YouTube. Mr. Robinson back here with yet another brand new exciting video, all math-based of course, and as always, it is an honor and a privilege to be serving you here today, as it is every day here in my virtual classroom. Step one aside as we jump into the Chapter 7 review in the Big Ideas Math Integrated Math 3 textbook, where we have 33 questions regarding sequences and series. Now, IM1 did a lot of things with sequences, including recursive sequences, which is section 7.5 on this one, but no matter, we're here in IM3 with a few more things to cover, specifically series, and some more challenging questions along the way. Hopefully all of it just means that you understand this very well. And if you don't, that's what the solution guide video here is for. So jump to the description section down below if you'd like to find a PDF of these 3 pages, as well as graph paper if needed for specific problems, and a timestamp for each individual problem and or section, all 5 sections that we have here, and all 33 questions. Without further ado, I'm going to go ahead and get started. We are going to start with section 7.1, where we are defining and using sequences and series. Now, this came before 7.2 and 7.3, where we had arithmetic and geometric specifically, but if this hits anything arithmetic and geometric based, I'll still mention it for what it is. I did at the time, so since we're hitting a review part anyway, it makes sense that we can also retroactively use those names, I suppose. Now, the first example that we have is covered, the only example in this set that we have is covered right here, where they say find the sum given this sigma notation set. Now, this is called sigma notation or summation notation because it uses the Greek letter sigma, and sigma represents something regarding summation, taking the sum of different terms. Now, each term is represented by substituting certain values in for I. We actually start with this lower bound here of 1. It needs to be an integer value. And then it goes up by increments of 1 up until the final value here. And we're going to add those different expressions together. So we're going to substitute 1 for I to get I squared minus 3. And then we're going to add, counting I up to 2, 2 squared minus 3, plus 3 squared minus 3, plus 4 squared minus 3. Ultimately, it ends up being those 4 terms for that series that we add together to become 18. And I don't know if I had mentioned that this is a series, given that we are adding these terms in a sequence. These would be the specific terms -2, 1, 6, and 13. Adding them together makes the series for that sequence. Anyway, there's no specific formula that we can do for this one because of that -3 that's involved, but there are some with a basic quadratic of I squared or something like that where we have other formulas to use. Given that this was only 4 terms, this is a pretty simple and practical way of doing this anyway, which is what they would have wanted. Okay, let's begin with question number 1. It says describe the pattern shown in the figure, then write a rule for the nth layer of the figure where n equals 1 represents the top layer. I don't know how big this shows up on your screen, so let me copy and paste this here. Okay, so it says describe the pattern shown. I don't know if that means in words. I'll go ahead and attempt to do that with you guys as an overall, but this is, this is n equals 1, n equals 2, n equals 3, and n equals 4. As an overall, we could count how many cubes, but we could also look at the rows and columns. Let's see, the length and width, if you will, because we can see this as this is like a 2 by 1 all the way down to, well, that 2 and 1 is pretty close. 2 by 1, and it goes all the way down to being a 5 by 4. I actually thought these were going to be squares, but I saw that top row and it was a little different. So the layer 1 has a width of 1 and a length of 2. Layer 2 has a width of 2 and a length of 3. The length is always 1 more than the width, and the width is equal to the layer number. In each layer, the width is equal to the layer amount, to the layer number, and the length is 1 more than the width. Does that work? So there's that. They do say write a rule for the nth layer. So what I'm really seeing for myself is for any row n, that's too big of an arrow. For any row n, I have a width of n and a length of n plus 1. So based on that, we can say this is an a sub n set. How many cubes are in there? Is that where they say? Is that what they're talking about for the pattern? Yeah, basically for how many cubes are in each layer, we are multiplying width by length. This could be proper right here that we could say. We could also say n squared plus n if we distribute it. Now, I never actually did a true count of these things. I wonder if I could devise that for myself, but it helps to have the physical set that's there. So the actual things, the first layer has 2 cubes, and then it is a 3 by 2, which is 6, and then it is a 4 by 3, which is 12, and then it's a 5 by 4, which is 20. Now, what we would often look for in a situation with these layers is, does it have a common difference? Does it have a common ratio? Does it have any sort of mathematical pattern you can determine? This one might be a little bit trickier because there is no common difference from the first set, but because it's quadratic, the second differences are constant. So we're adding 2 each time. This goes to show that it is quadratic, and then that might give you some time to figure out what this thing is. So n squared plus n truly works here. 1 squared plus 1 is 2. 2 squared is 4 plus 2 is 6. 3 squared is 9 plus 3 is 12. 4 squared is 16 plus 4 is 20. And that would continue forward, but that is the answer. Okay, number 2, write the series using summation notation. Also number 3. But for number 2, we have 7 plus 10 plus 13 plus dot, 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 all the way to 40. Summation notation is what we were talking about before with this sigma set. What we need inside here is this quantity set to represent each individual term that we would have. Like 7 is the first term, 40 is the last term, things like that. And we'll go from substituting in 1 all the way to how many terms there are in the sequence. So the most important thing for us is to recognize what kind of pattern it has. In this case, it has a common difference of 3, which means this is an arithmetic sequence. Given that it is an arithmetic sequence, we can use the explicit rule to figure out whatever term's value is based on its position. Therefore, this is like an a sub n equals first term plus common difference times n minus 1. When you distribute 3, you get 3n minus 3, or 7 minus 3 is 4, so we get 3n plus 4 as the thing. This is not the answer, but this is what we're going to have in substitute. Excuse me, not substitute. This is what's going to be the quantity expression in that sigma notation set. So when we write our full final answer here, and we're not quite done, we still have to figure out how many terms there are, but when we write our final answer here, it would have this sigma notation. I'm going to use a temporary variable I, and we're going to go all the way up to some number here. We still don't know what that is, but this is going to be for 3i plus 4. That way, when we substitute 1 in for I, 3 times 1 plus 4 is 7. When we plug in 2 for I, 3 times 2 plus 4 is 10, etc., and it keeps going all the way till we get to 40. Now, you could guess and check until you get this answer. You could keep adding 3 each time until you get to 40 and count it up. You could also use your explicit rule. 40 is the term a sub n, where n is the term position you're trying to look for here. So in substituting this, we can subtract 4 and divide by 3, and we get n equals 12. This is how many terms there are. This is what would go inside here. So I'm going to get rid of that little loop guy there. And this is going to be our final result. Here's summation notation for this guy. We go from the first to 12th term, 40 being the 12th term, of this set. Number 3, we get to do the same thing again, only this time it might be a matter of a different kind of rule because this does not look like a common difference. So on number 3, I have 0 plus 2 plus 6 plus 12 plus, etc., etc. Definitely not arithmetic. In fact, this might appear to be quadratic like the last one, like number 1. So it stands to show what we just practiced last time. We saw that there is a constant second difference of these. So given that it's quadratic, we can look into some sort of n squared something something. Now, I'm not really good at discovering these for you guys unless I do some sort of system of 3. I mean, I'm good at discovering it for myself, but teaching how I do it. But I'm really just looking at, if you substituted 1 for n, how could we get 0, given that it's some 1 squared thing? So, 0 can come to be, 1 squared minus something, right? So far, 1 squared minus 1 would actually work. How would you get 2 from 2 squared in something? Minus 2. This would actually work. 6 is 3 squared minus 3, etc. And 12 is 4 squared minus 4. Given that our nth term, a sub n, rather, a sub n would be n squared minus n. So it's really close to the other one, which was n squared plus n. And, sometimes it takes me longer to figure out what the thing is. But if you start writing out patterns for what one does and see how you can make it follow in some other way, this was pretty natural, easy growth there. Now, that being said, this is what we're going to place into this thing here. This shows this infinitely, by the way. There is no final term. Therefore, when we're using this, this is an infinite series. That's not a very well drawn thing there. We're going from 1 to infinity on this one. From 1 to infinity. And we have that then therefore as I squared minus I in that set. Now, there are alternatives you can do. You don't have to start with 1. I could start with 0. Like 0 could just be 0 squared, I guess, plus 0. I guess that would make it a little stranger to talk about. Like this could be written instead as 0 well, actually, how would this work? This would be 0 squared. If I plug in 1 here, though, that's not 1 squared. This could be 1 wait, is this the same sequence as before? Oh, it is. 2, 6, 12, 20. Okay, this could be like 0 squared plus 0, 1 squared plus 1, 2 squared plus 2, 3 squared plus 3, etc. And you'd have n squared plus n. However, for the sigma notation, you'd be starting from 0 and going to infinity of I squared plus I in that scenario. That's another alternative you can do, but you'd have to start from I equals 0. I'm mentioning that because we will be able to see that in some problems. I'm looking at numbers 4 to 7 and I don't see it. I actually see an I equals 2 on this one though, so that's a little different. But that's an alternative answer. I'm going with this one personally, just for like canonical reasons. Okay, numbers 4 through 7, we are finding the sum. Now, number 4 has no real basis for some smaller formula we can use to simplify what we're doing here, but we are trying to find the sum of these terms. We're going from term 2 to 7. So this is, again, one where we're not starting from 1 from here, but we are going to substitute 2 into here, and then 3 and 4 and 5 and 6 and 7 and add those up. So this is going to be 9 minus 2 cubed plus 9 minus 3 cubed plus 9 minus 4 cubed, 5 cubed and 6 cubed and 7 cubed, etc. Now you have to give me a moment here. You know what I could do to make this a little bit easier for myself is there is a 1, 9, 2, 3, 4, 5, 6 9s added together. So I'm just going to say it's 6 times 9 there. And then minus all of these guys added together. And actually, I'm going to come up with what those are. 2 cubed, because I'm trying it without a calculator here. So I have 8 plus, remember, all these are subtracted. We're adding the negative, so we're subtracting the sum of all these. 8 plus 27 plus 64 plus 125 plus 216 plus 343. So that's going to be 54 minus 35, 99, 224, I believe. It's 224, 540, and 783. 54 minus 783, which is negative 729. You can use a calculator, that's fine. I just wanted to clean it up a little bit. So yeah, I could have done 9 minus 8, which is 1, and then we could have written out what the actual terms are, because those would be the actual terms of it. And remember, that's the second term that we start with, not the first term, but that should be our sum. Okay, however you want to choose, that's up to you. Number 5. Now, number 5 is an interesting one because it looks like we have 46 terms to add together. So we're going from 1 to 46 of I, which means I'd plug in 1 for I, and then 2 for I, and 3 for I, etc. And I'd add these up all the way to 46. Now, we have some options in what we can do here. One of them is this, given that we're in section 7.1, you hadn't yet learned arithmetic series until 7.2, but you could use the arithmetic series formula because this does have a constant difference. We're not going to do that, though, just because it's not section 7.2. We're going to do it in section 7.2 anyway, so we're fine. The second thing is there is a formula that's used for this, which can be born off of the arithmetic series formula, the actual rule, that if you're doing it from I up to some term n, you can take n times n plus 1 divided by 2 in this scenario, and representing how many terms there are, or the last term in this case. So what we can do here, instead of literally adding all those together, instead of using the arithmetic series rule, is we can say this equals n, 46, times n plus 1, 47, all divided by 2. 46 over 2 is 23, and 23 times 47, I don't know off the top of my head. This is where I have to probably go to the calculator here. Let's go to the calculator. I can pretend like I know, but I have to pop it up at some point anyway. Let's do it now. Give me 1 second. Okay. So we are doing 23 times 47. And we have 1081. So this is the sum of the first 46 positive integers. Oh, you can't see what I wrote. It's the sum of the first 46 positive integers. Isn't that something you always wanted to know? Because I didn't. I do for the problem. Number 6. This is the sum of the first of the squares of the first 12 integers. So again, you have options here. This would basically look like 1 plus 4 plus 9, etc., all the way till 12 squared. Now, given that this is not an arithmetic series, we couldn't use that formula to begin with anyway. But this one does have its own formula, particularly for quadratics. This one was n times n plus 1 all over 2. If it's squared, it's n times n plus 1 times 2n plus 1 all over 6. Is that right? I think that's right. All over 6. So we can use this version of this, given that we're going from the first term to that 12th term. So I can substitute 12 in that way. And with me explaining this the whole time, you're like, Mr. Robinson, I could have typed this faster in my calculator. I get it. But what if this wasn't 12? What if it was 1200, right? It depends on how big it gets. So we're going to be doing 12 times 12 plus 1 times 2 times 12, 24, plus 1 is 25, all over 6. That's pretty big numbers overall. 12 over 6 is 2. 2 times 25 is 50. 50 times 13 is 650. No calculator there. Okay. Number 7 has no real rule we can work with, so we're just going to do the substitution of these 5 terms here. So we're going from the first to 5th term of the sum for this quantity. So we're going to do 3 plus 1. You know what? I'm going to do these more so in my head. Well, I'm going to write out what they are. So plug in 1, you get 4 over 2. And I don't want to make that 2, actually, because I want to combine not combine like terms. I want to use a common denominator here. Some of these are going to be fractions. You plug in 2, you get 5 over 2. You plug in 3, you get 6 over 2. Plug in 4, you get 7 over 2. And plug in 5, you get 8 over 2. So I can add all these up on top, kind of divide them by 2 later, right? 9, 15, 22, 30, and 30 over 2 gives me 15. Kind of easier to do that than to make these separate in that way. Okay, that is the end of section 7.1, where this was like any sort of special cases, including quadratics, and this kind of, well, I guess this isn't rational, but it had a fraction in it. A lot of different things that can happen there. 7.2 is focused specifically on arithmetic sequences and series. Now, before we start number 8, let's take a look at the example that they bring up. This was stuff that, like I said, might have been done in IM1 a little bit until you hit series. But this example question is something you would have done in IM1. Write a rule for the nth term of the sequence, 9, 14, 19, 24, then find a sub 14. So it is an arithmetic sequence, not only because we're in the section, because it has a common difference of 5. They're showing that by subtracting one term by the one before it. I think most people, you could tell that we're adding 5. The first term is 9. For our rule, we need both the first term and common difference to write the thing out. They write the formula slightly different than I do because I put the D in front. I don't like having a monomial in back multiplied by a binomial. Anyway, you substitute 9 and 5 into here, and they distribute the 5 and combine like terms with the 9. We did this actually on a previous problem on number 2, I believe. So, and that's kind of the point that I was making from before, is we wrote these rules out without actually being taught it yet, even though you would have done it in IM1. But we're simplifying this thing, and it's 5n plus 4. To find the value of the 14th term, you're going to have to substitute 14 in for n, and you get 74. Now, we are going to be dealing with series, which means we're going to deal with the arithmetic series formula, and I'll go ahead and give that to you when we hit a question regarding it. Question number 8 says, tell whether the sequence here is arithmetic and explain your reasoning. What we're trying to ask is, do we have a common difference? Now, the way that the book would want you, I'm not just saying book, I'm just saying the way that it's instructed. The way that they would want to instruct this to you is you have to figure out what you're adding or subtracting each time and if it's constant. And they would say, if you can't tell what it is, which we probably can, if you can't tell what it is, subtract a number by the one before it. Does 4 minus 12 give you the same thing as negative 4 minus 4, negative 12 minus negative 4, and negative 20 minus negative 12? confusing as this looks, we get -8 from each of these. So we do have a common difference of -8. I think most people can establish, if I asked you, it was 4 minus 8, -4, yes. Subtract -8 each time, yes. Because we have a common difference of -8, it is an arithmetic sequence. That is the reasoning for it. That's what you're trying to justify. This mathematically justifies it very well for us, though. Number 9, or numbers 9 through 11, they say write a rule for the nth term, then graph the first 6 terms. So I'll be using graph paper for those. So 2, 8, 14, and 20. They do call them arithmetic sequences. We're aware that that's what we're going to have. Writing the rule is akin to what you saw up above. We do need the first term, which is 2. The common difference, I'm not going to sugarcoat it. We just know it's going to be 6 here, adding 6 each time. So your rule is going to be taking 2 plus 6 times the quantity n minus 1. This could be the final rule, but we're going to distribute that 6 to get 6n minus 6. And 2 minus 6 is -4. So we get 6n minus 4. Now, say write the rule and graph the first 6 terms. I don't really need the rule to get the next 2 terms. I'd rather work this recursively, which is a word we're going to be talking about a lot more in section 7.5, where I can add 6 to get this next term. 2, 8, 14, 20. Plus 6 is 26, plus 6 is 32. So these are the ones we're going to be plotting on a graph. Now, given that it's a sequence, you know, sequences, give me a second, I'm trying to pull up my graph paper stuff. Sequences are discrete in that you don't connect the dots of your things. It's the first term, and then the second term, and then the third term, things like that. So that's just how we work off of it. And we also start from the first term. So the first term is when n equals 1, and when n equals 1, we have a value here of 2. I'm going to have to change my scales, actually. Let's go by 4s so we can hit this right. 20 and 40. So here's 4, so half of 4 is 2. The first term is 2. Second term is 8, that's 2 4s. And then 14, it's kind of like up 1.5 over 1. If I just want to do it that way, I can actually hit these values. Here's 26, and here's 32. And that's our graph. That's all we do. Arithmetic sequences will be linear in nature. They have a linear relationship given the common difference. It's kind of like a slope. I mean, it is. It's like a slope. This is like y equals mx plus b straight up. Even -4 would have been that y-intercept there, although that's not one of the terms in the sequence. So that is number 9. Let's jump to number 10. Now, number 10 is not written, and I'm glad they have this. I forgot that this kind of existed for a second. Number 10 is not written out as a sequence. They give you information, and we have to use, that information to come up with not only the rule, but those first 6 terms. Now, there are ways that you can work your way back to get those 6 terms. Like, if the common difference is 3, by the way, they're saying that the 14th term is 42. So the 15th term would be 45, and the 16th term, you'd be adding 3. So if you wanted to go backwards, you could subtract 3 over and over. The 13th term is 39, and the 12th term is 36. Actually, now I know what the rule is. That being said, we're not going to go about it that way. We're going to do this more like what you would in slope-intercept form, that kind of thing. We have the 14th term. So the 14th term being 42, that's born from taking the unknown first term that we have, plus the common difference times n minus 1. And 14 minus 1 is what we have there. We're using this formula right here. We're using this formula, but we're using it to solve for the first term. That's what we need for our rule. First term and common difference. So 3 times 13 it is. And that's 39, and you subtract 39 from both sides, you get a first term of 3. So your rule is going to be 3 plus 3 times n minus 1. One simplified, you distribute 3n minus 3. 3 minus 3 is 0, so you just get 3n. I started to notice when I said the 13th term is 39, 12th term is 36, that it's just 3 times whatever term you're looking for. So that's the rule, and then we have to come up with the graph of the first 6 terms. First 6 terms meaning first term is 3, and then you keep adding 3 from there. 3, 6, 9, 12, 15, 18. So let me write those out. 3, 6, 9, 12, 15, 18. Okay. Let's scale by 2s. And here we'll have 2, 3. This is kind of up 1.5 over 1 again in its own scale and from its own starting point. And there you have it. Okay, number 11. Number 11 goes a little bit deeper into it in that you don't even have the common difference this time. So this time you need to find that common difference as well as find the first term. Now, I bring this up because some folks get too deep into the, wait, what do I plug in where? What's that formula? Oh, what's the thing I got to memorize? You have to remember these are arithmetic sequences which are like linear equations. This would be akin to writing the equation of a line that passes through the points 6, -12, and 12, -36. These are the x's basically. The n is like your x's and the a sub n's are like your y values. You need to find the slope and the y-intercept. I could literally do it in that fashion, and I will do it in this fashion afterward. But you can literally do it in that fashion for this one. Same with the previous problem. Previous problem, we kind of had the slope, and we had a point on the graph. We could start with point-slope form and work it that way. We could use y equals mx plus b. A lot of different ways to understand this stuff as long as you make sense of that. And furthermore, we have to find the slope. So, y2 minus y1 over x2 minus x1. Am I right? So what I'm going to do to begin with, though, is kind of their fashion of it, where we need a sub 1 and d. We're going to create a system of equations out of this, where we use that, formula, a sub 1 plus d times n minus 1. 6 is this n this time. 6 minus 1 is 5. So let me write this actually as 5d instead. And this one, -36, equals a sub 1 plus 12 minus 1 times d, and that's 11d. So we have these two sets here. If we subtract down these lists, that means these signs change overall. We get -12 plus 36, which is 24. A sub 1 minus a sub 1 is 0, and 5d minus 11d is -6d. Divide both sides by -6, you get d equals -4. Now we can substitute into either one of these. It's a system of equations. Now you can substitute into either one of these equations, like the top one, for d to solve for a sub 1. Whoops, plus 5 times -4. That is -12 equals a sub 1 minus 20. Add 20 to both sides, you get 8. So that's the first term. So your rule is going to be a sub n equals 8 minus 4 times n minus 1. That's the quantity. Distribute -4 into there, you get -4n plus 4. 8 plus 4 is 12, so we get -4n plus 12. There's our final result. Now we're still going to graph that and all this. Let me show you the alternative version using like a slope-intercept form, point-slope form, whatever kind of form you want to look into. Treat it more like the y's and the x's and stuff like that. Your slope, d, your common difference, is taking, y2 minus y1 over x2 minus x1, which is 24 over -6, which is -4. Where have we seen this before? 24 divided by -6. Oh, that's right. I divided 24 by -6 right here to find -4 for d, because what you're finding is the distance between these two values. The distance from -12 to -36, or the other way around, is 24. As we go from 12 to 6, so we're going 6 down in that way. That's how many terms they're spaced across, and that's how far their difference is. So we're finding the average, how much you're subtracting from one term to the next is your common difference. That's like your slope. Down 4 over 1, subtract 4 for every next term you go. And then you can substitute that into, you can use, this is y equals mx plus b, right? This is y equals mx plus b straight up. So we need to find that 12. That's kind of your a sub 0, actually. It's your 0th term. It's not your first term. We haven't found out the first term yet, by the way. Oh, well, yeah, we did. It's 8. It's not your first term. Your thing is 12. So we can say, like, take a point, like -12, y equals mx plus b, and then you have -12 equals -24 plus a sub 0. Add 24 to both sides, get a sub 0 equals 12. And then you get all that stuff all over again. So you're right back to where we were without needing the simplification of that aspect. It all works out. It's your choice on how you want to go ahead and do that. Anyway, we still need to graph these, and we still need to find all the values. Our first term was 8, so we go from 8, and then we keep subtracting 4. 8, 4, 0, -4, -8, -12. And we knew -12 was the 6th term, as it showed up right there. So we have to graph these ones. I need to actually now use the 1st and 4th quadrant this time, so let me get a little bit more involved with my graph axes. That's too big. Okay. I can pretty much scale by ones here. Negative 12 will fall slightly off, but that's okay. So the first term is 8. Second term is 4. Third term is 0. Fourth is negative 4. Fifth is negative 8. And sixth is negative 12. So it falls off just a little bit. 10, 11, 12. As long as it forms the linear path there. Okay, I spent a lot of time on those problems to kind of give you process and different alternative methods and how you can approach them. And I want you to kind of keep those in mind when you're doing it, because you memorize, you're going to mismemorize. You're going to forget later on. And, you know, it's just things where, what are you truly learning then, right? My goal here as a teacher personally is get you to learn. Whether or not you care about what aspects it is that you're learning, it's about math mindset, right? Not just acquisition of knowledge. Anyway. Find the sum here from 1 to 36 of terms 1 to 36 of 2 plus 3i. Now, keep in mind what this would mean is you'd be substituting 1 into here. 1 is 2 plus 3, which is 5. When you plug 2 into there, it's 2 plus 6, which is 8. It looks like it has a common difference of 3. You'd be adding 11. Whoops, I need not commas, but pluses. You'd be adding 11, etc. And you'd be doing this all the way until the last term, which is 2 plus 108, 110, right? You're doing it all the way till then. And by the way, I need to compute that for you officially when we talk about what we're going to talk about here, which is a lot of addition. Now, there's no shortened formula for this specific instance except for the fact it's an arithmetic sequence. So because of that, we do have a rule. And that rule is the sum of those n terms pairs up all your n terms and you multiply your first term added with your last term. You multiply by the sum of your first term and last term. So that's why I said we need to know what that last term is. Now, the number of terms is 36. Your first term is, again, 2 plus 3 times 1, which is 5. We already have that. And the last term I got here was 2 plus 3 times 36. 3 times 36 is 108. 2 plus 108 is 110. So these are the three variables we need, 36, 5, and 110. So this will be the sum of these 36 terms to be 36 over 2 times 5 plus 110. 36 over 2 is 18. 5 plus 110 is 115. And 18 times 115 is left for the calculator. Where I'm getting 2070. That is the sum of all these terms here. And that is using an arithmetic series with the formula. Okay, number 13. Word problem. You take a job with a starting salary of $37,000. Your employer offers an annual raise of $1,500 for the next 6 years. Write a rule for your salary in the nth year. What are your total earnings in 6 years? Now, there are two questions within. One is an arithmetic sequence question. One is an arithmetic series question. Your first year on the job, I guess they're 37,000 considered to be the first year, your starting salary, first year, the nth year. Yes, your starting salary, your first year on the job is 37,000. Your common difference is 1,500. We know it's a common difference because we're adding 1,500 each year. So we can write a rule for this. This is kind of our part A for the nth year. For any year n, we have 37,000 plus 15,000 or 1,500 times n minus 1. I'd like to add 15,000 a year. That'd be great. Which is 37,000 plus 1,500 n minus 1,500. And 37,000 minus 1,500 is 35,500. So 1,500 n plus 35,500. So that's the first part. That's arithmetic sequence based. So in the 10th year, I could plug in 10 and figure out how much I'm making for that year. They do ask, what are your total earnings in 6 years? So they're not asking how much money you make on the 6th year. They're asking, what is the sum of those 6 years? Now, 6 terms is not very much when it comes to, I could put what all those are together. But as far as practicing that sum formula, we did need first term, we do need number of terms, and we do need the value of the last term. So let's use that rule, 1,500 n plus that. Whoops. And we'll just use the formula for that. Again, it might be faster to do something else, but for the sake of practice and for times when it will be faster to use this, let's go ahead and do that. So I calculated this and got 44,500. So here's your A sub 1, here's your n, here's your A sub n, your A sub 6. So the sum of the first 6 terms is going to be 6 over 2 times 37,000 plus 44,500. 6 over 2 is 3. I don't want to botch this one, so it should be 81,500, but let's check. 30. It is 81,500. And I don't want to botch this one either. It should be 244,500. 244,500. 244,500. So $244,500. About $250,000 after 6 years. Which is great. It just keeps jumping up, right? This is how much money you started with, 37,000, and year 6 you're making closer to 50,000, right? Pretty soon you'll get to that 50,000 by year 10. Okay. Let's go to section 7.3 with geometric series, but specifically we're going to talk about finite geometric series when we do, because 7.4 is going to be infinite. Now let's start with our example. Find the sum here, and this is geometric. We can tell given the exponent contains the variable, and this has that. We haven't covered anything geometric just yet, not even in section 7.1. It didn't actually hit, so this is our first instance in the review of talking about it. This is your first term times your common ratio to the I minus 1 power. As long as it's a minus 1, this will be your first term, and this should always be your common ratio. So they're establishing by plugging in 1 that they're getting that 6 and common ratio of 3. We do need those two values for your formula, and you need to know how many terms, which is 8 terms from 1 to 8, to find the sum of these ones through the formula without using a practical approach. So they're using it here. This 8 would have been n for your formula. It's a sub 1 times 1 minus r to the n power, all divided by 1 minus r. They're plugging in their numbers. They went to calculator. I imagine I'd do some calculator at some point, but I like to simplify parts beforehand. And they're getting 19,680. So they're literally doing 6. If you imagine how this common ratio set works, the next term is 3 times more than the previous term. So this would be 6 as the first term, then 6 times 3 is 18, and then times 3 is 54, times 3 is 162, times that is 486, and times that, 486 times 3. Oh, I'm not going to do all of them, I guess, but you're doing that all the way till your last term, which is whatever. We're adding those up. Now, a series, I don't think I ever mentioned this, but although you have a common ratio for a geometric series, geometric sequence, where you multiply things, the series still adds them together. It's not like we're suddenly multiplying our terms together, just the common ratio is you have to multiply from one term to the next. Okay, so they get their sum there. Let's go ahead and get started with our problems. Let's go to number 14. Tell whether the sequence here is geometric and explain your reasoning. Now, it's not arithmetic. It won't have a common difference, but we got to see if it has a common ratio. Our test can come twofold. You can either determine what you're multiplying by straight up, just kind of a guess and check instance, like 7 times 2, etc. So is this times 2 each time? I think we can establish yes, 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 yes. Given that, we could say our common ratio is 2. If you needed to test for yourself, you weren't sure what your number is, it gets a little too wonky, you divide one term by the one before it, in which case we would also, once again, get 2. Just like for the arithmetic set, we subtracted a term by the one before it to find the common difference. But this is yes, this is geometric, this is our justification, common ratio is 2. Numbers 15 to 17, we're going to write a rule for the nth term of the geometric sequence, then graph the first 6 terms. Now, this is like the arithmetic stuff we did beforehand, only we have a different rule to represent. However, the next questions afterward remind me a lot of that arithmetic stuff we were just talking about. So we'll do it for geometric bases. 25, 10, 4, and 8/5. This is a perfect example of what are you multiplying from one number to the next. You might know what you're dividing by, I'm not sure, but we have to determine common ratios, what you're multiplying by. So once again, your common ratio in this set, you are dividing a term by the one before. 10 over 25. You could do the decimal. I'm going to prefer to do the fraction of 2/5. So we're multiplying by 2/5 from one term to the next. They're saying write a rule for the sequence. We need the first term, which is 25. We needed the common ratio, which is 2/5. They all use the numbers 2 and 5. So your rule is a sub n equals, we take the first term times the common ratio, raised to the n minus 1 power. Or you could use 0.4. Again, this had a fraction, so I'm more likely to use a fraction myself, if so. Number 16, they give you the value of the fifth term and the common ratio. And common ratios can be negative, as signs would alternate. Oh, I'm not done. I'm sorry. Let's go back. We have to still graph the first 6 terms. Let's go back. Let's go back. I think I graphed all my other ones from the arithmetic, right? So we have 25, 10, 4, 8 fifths. The next 2 terms, we got to multiply by 2 fifths. 8 fifths times 2 fifths is 16 25ths. And that times 2 fifths is 32 over 125. Now, what those numbers are exactly, well, this number is exactly 0.64. I don't know what that number is exactly. So this is 1.6, this is 0.64, and this is 2 fifths of that number. I don't know. It's going to be something close to like 30 or 0.3, I should say. No, close to, no. Close to, this is close to a quarter, so close to maybe 0.26 or something like that. That's going to be my guess-ish, so about a quarter. Now, when it comes to plotting these on a graph, I'm still going to use the same graph axes as before, so you don't have to print out 2 different sets. You know, sometimes I use that scaled square graph paper, which I'm going to keep using. Sometimes I use the tall graph paper. So I'll keep using the scaled bits here. I do need to change the scaling, however, so that I can fit 25 on there, but not make it too big. I don't want to go by 5s. If I went by 3s, I guess these numbers will get a little weird with that, but why not? At least they'll fit. So I'll do 15 and 30. So 25, this is 18, 21, 24, 27. So 25 is a third of the way from 24 to 27. That's the first term. 3, 6, 9, 10 is a third of the way from 9 to 12. 4 is a third of the way up from 3 in this instance, given the scale. 16 25ths is 0.64. At this point, it's, 1 is a third of the way up from there. These ones basically get really small. I'm just going to plot what I plot there. Oh, did I skip one? I'm sorry. 1.6 was the first one. 1.6 is about halfway up to 3, just a little bit more. And then it gets pretty small after that. Like here, and pretty much like here. Geometric sequences are like exponential functions. This resembles exponential decay. Given that r was a number less than 1, the values will shrink towards 0, and that's what you're seeing there. Not linear, exponential. And speaking of, when we hit number 16 finally, all of these things are exponentially based, whether we know it based on a rule or what have you, and it should remind us of something we had done in the past on coming up with equations of exponential functions based off specific information. This is like finding the equation of an exponential function given a point, 5, 162, and your multiplier is -3. Now, what we have is the rule set a sub n equals a sub 1 times r to the n minus 1 power. Let's plug these things in. 162 is the fifth term. We need to find the first term based off knowing we have a common ratio of -3, and 5 minus 1 is 4. -3 to the fourth is positive 81. Let's do a sub 81 times a sub 1. Divide by 81, you get a sub 1 equals 2. And there are a bunch of other ways you can do that, right? We can divide by -3 going the other way. And that would actually have been helpful because we got to write the first 6 terms anyway, but we are writing the rule. So a sub n is 2 times -3 to the n minus 1 power is the official rule. 2 is the first term. We have to get the first 6 terms as we plot them on a graph. So 2 times -3 is -6, and then multiply by -3 over and over. Here's that fifth term of 162. There it is. And then the sixth term is -486. So we got to plot these on this graph. Clearly, by my scale, oh, I need to use both positive and negatives. Hold on. But clearly, by this scale amount, I'd like to go to positive and -500. I don't generally like graphing these geometric ones just because the scale gets so... I have to stretch the scale out so much that a number like 2 or 6 or even 18, those numbers are barely going to be sizable on here. Like, I'm just pretending like I'm plotting them in the right spot. So, we just do what we do. I'd almost rather start from the bigger numbers just to give you the picture of what we have and then shrink afterward. But that's 500. That means that we're going by 100s each time here, like that. That means this is 250. And then this is negative 500 down here because I got to fit that negative 486. But it's going to kind of look like that for the 100s. This is negative 250 right there. So negative 500 is kind of the first one I want to, or negative 486. That's the sixth term. Boom. So I want to plot negative 486 first. This is negative 400, negative 450. So negative 486 getting pretty darn close to negative 500. Then we go to positive 162. 50, 100, 150. And 162 is, a little bit up from there. You can see the shrinkage already happening here. Negative 54. Here's negative 50. So negative 54 ain't far from it. Getting pretty close now to the bottom. 18 is only about 2/5 up to 50. So looking at about that. And negative 6, yep. And 2, yep. So getting pretty short. I mean, why they have us graph, I don't know. Now, Mr. Robinson, this doesn't look exponential. Yeah, that's because the signs are changing. If they were all positive, you'd see a curve kind of upward like that. So this isn't a true exponential function because exponential functions couldn't have negative bases. It's a true geometric sequence, but this isn't one where if it was exponential, you wouldn't be connecting dots and oscillating up and down like that. All right, let's do one more for these things where we have to graph them. And then that would, I don't know if we have to graph any more after this, but that would be 6 graphs total. So if you're printing out the graph paper, just print that one side. Maybe you'd be good. So the third term is 16. The fifth term is 256. A lot of different ways you could play with this thing, especially since we have to write out the first 6 terms. We could even think of it in terms of this. There's one danger to thinking about it this way, and I'll call it out in a moment. But yeah, this is the third term. This is the fifth term. So you're kind of trying to figure out, I'm giving you just a practical version in case you don't know what to do otherwise. 16 times some common ratio twice gives you 256. So, right? 16 times r squared is 256. Never mind, there's no danger this time. If I divide both sides by 16, I get 16 and take the square root of r, you get plus or minus 4. This is the thing I wanted to bring up. This could be positive or negative. So, I kind of want to use this practical approach because we got to build up the first 6 terms anyway. Then I'll go backwards and find another way to write your rule for you. However, we're not yet done. We still have to find the first term. And again, you could go practically with this. If I multiply by positive or negative 4 going this way, then I could divide by plus or minus 4 this way to get these other couple terms. Now, what's interesting about this is they are asking us to graph these terms, given that they can be positive or negative in some instances, and I'm going to talk about that more in a moment. There are 2 different sets of graphs we can make. So, interesting. I didn't really think about that for this problem yet. But dividing by positive or negative 4 gives you positive or negative 4 as a value, and then dividing by it here gives you 1. Understanding that if we don't like divide by negative 4 this time and then positive 4 the next time, we either divide by positive both times or by negative both times. So this will absolutely only be a 1. There's no other, it can't be negative 1. This one can be either positive or negative 64. If you're multiplying by positive 4, then it's positive 64. Multiply by negative 4, and it's negative 64. But then you get the positive 256 all over again. And then plus or minus, or times plus or minus 4 again is 1024 here. As far as the rule goes, it's going to be a sub n equals 1 times 4 to the n minus 1 power. Now, I don't need the 1 specifically because 1 times anything is just that value, so we could write this as the answer. No parentheses would be required given that this is a positive integer, so we could just write it as 4 to the n minus 1 power, boom. Or it could be negative 4 as the common ratio to the n minus 1 power. The first term would still be 1. So 2 different answers there. Now, I did that in a way that wasn't like how the textbook would say it. Maybe your teacher's like, what are you doing? It's like, well, I'm using logic to do this. I needed the first 6 terms anyway, so that kind of works. How could we do it alternatively? You could build a system of equations with the 5th term and the 3rd term. You know, the 5th term, 256, is the first term times the common ratio to the 3 minus 1 power, or 5 minus 1 power, which is 4th power. And then you could do 16 equals a sub 1 times r to the 3 minus 1 power, or 2nd power. You could solve this using substitution or elimination. The book tends to do more of a substitution version. I much prefer elimination. By elimination, you would be dividing these two guys out. 256 over 16 is 16. A sub 1 over a sub 1 is 1. r4 over r squared. You subtract the exponents and you get r squared, and you're right back to where you were here. You end up getting r is plus or minus 4. Then you plug in either of those values into one of these sets, such as in this one here, you could do 16 equals a sub 1 times either positive or negative 4 works here, because when you square it, it turns into 16 regardless, and you get a sub 1 equals 1 in that light. So we could, let me keep that as purple. You could use that elimination method to get those two things, end up writing the equations exactly like that was. You could also use a substitution method being where you would get, say, a sub 1 by itself in this equation by dividing both sides by r squared. Then substitute that into your a sub 1 in this top equation where you get 256 equals 16 over r squared times r to the fourth. R to the fourth over r squared becomes r squared. 256 equals 16r squared, and you continue forward. You end up dividing by 16, take the square root. You get exactly what we saw right here. So you end up solving for r. Where did I write r as plus or minus 4? Did I erase it? Oh, I pointed to it up here. I see. So there are a lot of different stages to what you can do here. Now, when I solve for it there, then I could plug in plus or minus 4 straight into here. 16 over 4 squared is 16 over negative 4 squared, and you get it. So it's a lot of complicated things for me saying you can either do this, that, whatever. Hopefully, you've had your own version of what you did, either in kind of black right here, or blue, or purple. But we still have to graph these. We still have to graph these points right here. And there are two different graphs you can make. So one version of the graphs has all positives. Let's see how I do this. Should I do this on the same graph axes? Maybe not. Let me first use the first quadrant set only. I'm going to write this on the other side on this thing here, because I kind of ran out of room on that side. This is still number 17 continued, where we can either use 1, 4, 16, 64, 256, and 1024. Now, with this set, I'm going to scale by hundreds. So this will be 1,000. 1,024 is not going to be much more than 1,000 at all. So these are all going by hundreds. That means 1 is way down. It might as well just kind of be 0 right there. You can't tell the difference. Same with 4. It is so low down there. That's 4 1/100ths of a value. 16 barely makes a dent, even. 64 is a little more than halfway to that 100 mark. Then 256, we jump, right? 100, 200, 256 is right around 250. And then the 1024 shoots past 1,000. Barely, but it shoots past 1,000 like that. Maybe a little more than that. It's got to be a quarter way up to the next value, so probably like that. So yeah, quick shot up. It's exponential. It's exponential, and you can see that there. The alternative to this is using the ones where the signs change, right? We hit some negatives and such. So let me fit that here as well, where, give me a second. Let me move this over just a little bit, and I want to copy and paste those here. Now, some signs are going to change on these ones, right? So here we're going to have 1, negative 4, 16, negative 64, 256, negative 1024. So let me copy and paste the other kind of graph axes we have. I know this problem's taking a while, but this is either this or that version of these, right? Because you can do either, because there's no knowing whether that common ratio would have been positive or negative. I think that's the point I'm trying to make there. We don't know based off that. It's too ambiguous. They didn't give us enough information, so we're accounting for either instance of this. Okay, so that one, the 1 and the 16 and stuff, these are unchanged from what they were before. Positive 1, positive 16, positive 250. Oh, did this move over? Positive 1, positive 16, heck, positive 256. Those are all up here. But these other ones turned negative. Negative 4. Negative, what was this one? Negative 64. Negative 1024. So this is that oscillating pattern of these ones, unlike the last set, which was just straight exponential. This ain't truly exponential, but it's still a geometric sequence. Okay. I've gone pretty long in this review, but there are just a bunch of different ways to do problems. I'm only halfway through the problems. I don't know if the next half is longer or shorter, but a lot of graphs on those. Number 18, find the sum. So this will be a lot like the example one we have. Find the sum from I equals 1 to 9. Your only geometric series on here. Finite geometric series. Next is all about infinite. 5 times negative 2 to the I minus 1 power. So your rule is going to look like this. A sub 1 times 1 minus r to the n all over 1 minus r. I write it kind of like that. Your first term is 5. Your common ratio is negative 2, and we have 9 terms. We're going from the first to 9th terms. That's 9 terms total. This is what we're going to substitute in there. Sum of the first 9 terms takes your first term times 1 minus your common ratio raised to the n power all over 1 minus that common ratio. I like to clean up some things if at least I just want to clean up that denominator. 1 minus negative 2 is 1 plus 2, which is 3. Unfortunately, 5 over 3 don't reduce as anything. We're going to subtract negative 512. That's negative 2 to the 9th. So we're going to add 512 there. So I'm going to do some of the work right now. So that's 5 times 513 over 3. I believe 513 divides by 3. And it should, because these are all integer values. Your final answer should be an integer. 513 over 3... 71? I think it's that. So I think this is 71. So 5 times 71 should give you 355. Call the 355? Call the 355? No. Is it 355? 5 times... This isn't 71. It's 171. 171. So it's 855. 855 on that. Okay, that should be my... I was going without a calculator, so I hope that's right. Okay. 7.4. Finding sums of infinite geometric series. Now, we were doing finite geometric series. We only did one problem that had a geometric series thing. That's what I was saying. These first few problems are technically things we could have done in IM1, I suppose. Maybe these ones were more IM3-esque. Anyway, now we're doing infinite. Infinite will only apply provided that you have a common ratio that's between negative 1 and positive 1. 4/5 is between negative 1 and positive 1. Your values need to converge by becoming smaller and getting closer to 0 over time. If they don't, they diverge. They have no sum. But if they're like this, they do. And there's a formula for it. It's like this series formula we have here, only it's completely negating this 1 minus r to the n power. I'm not really going to talk about why, but it's a sub 1 over 1 minus r. You can only use it if r is between negative 1 and positive 1. So they're finding the sum. Let's see. Oh, we have to do another graph here as well. For this series, the first term is 1. Common ratio is 4/5. Oh, right here. How do we know the first term is 1? Well, you can plug 1 into here. Also, it still has that format, and this number that's invisible right there would be a 1. That's your first term. It's your common ratio. It's the two parts you need for the formula. So 1 over 1 minus 4/5 is 1 over 1/5, which is 1 times 5, which is 5. That's the sum of the infinite number of terms in this set here, where you're literally doing, if we're writing out once again what this thing is, it's an infinite set of 1 plus 4/5 plus 16 25ths plus 64 1/25 plus 256 over 625 plus, and it keeps going forever. The numbers are shrinking. Oh, you can't see some of these. The numbers are shrinking, but eventually they converge toward a value, and they equal 5 ultimately. That's what they're saying with that set. I apologize if I ever wrote something on this side at all and it got cut off because I don't notice. When did I must have erased it. Anyway, let's go to number 19. Consider the infinite geometric series here, 1 and then negative 1/4, etc. Find and graph the partial sums for n equals 1, 2, 3, 4, and 5. Then describe what happens to s sub n as n increases. So we do have to do another graph. This is one of my... This problem might take a little while as well. I believe that in the book, when we did problems like these in a section, we were fine writing out fraction versions of these, so it's not like I'm chasing common denominators. Now it says, consider the series. This isn't technically a series because it has the sequence of terms, but you have to be adding them to get them. So they ask for partial sums, like the sum of the first term by itself is just 1, And then the sum of the first two terms, you have to do 1 plus negative 1/4. 1 minus 1/4 is 3/4, which is 0.75. And you keep going from there. We need to find the third term, fourth term, and fifth term. The sum, of the first 3, 4, and 5 terms. So 1 minus 1/4 plus 1/16 will be here. 1 minus 1/4 plus 1/16 minus 1/64 is here. And then all of them together here. Now, this one has an oscillating pattern. That doesn't mean it doesn't converge. Because the common ratio appears to be negative 1/4, then it will still converge at some value. We'll figure out shortly what it is. I don't actually know. I'm going to guess it might be around 0.8. I mean, it'll approach some value that we're going to go like, oh, yeah, that's a classic case value. But what we have to do here is kind of use the calculator. I'm going to do 1 minus 1/4, which was 0.75, plus 1/16. That'll be this number. Then we'll take that minus 1/64. Oops. And that plus 1 over 256. I believe this is getting closer. As long as it teeters on opposite sides of your value for the plus and minus version of it, that means it is converging toward that value. So you can clearly see this conversion towards 0.8. That being said, I need to write these decimals out. There's 0.8125. Normally I round them. Let's see. This is around 0.7969. Sorry, I'm writing these first. And then 0.8008 if I'm rounding. So here are some of those values written out. We need to graph these ones. I'm still going to use the same graph axes as before, like this version. My scale can totally change. Instead of going up to 10, we'll just go up to 1, right? So this will go up to 1 for the following values. And this is 0.5, 0.5. So this is, we start at 1. And then we hit 0.75, which should be halfway in between. Remember, these are sums, by the way. These aren't the terms themselves, just the sums. And then 0.8125, I don't know, 1/8 of the way up to there. And it's really going to shrink here. It's going to be very hard. 0.7969, I mean, yeah, and then just above it right there, you can see it converging toward 0.8. That is the value of convergence in this case here. Boom. There's the 0.8. So we're saying, they say, describe what happens to S sub n as n increases. Remember, this was only a partial sum as well. This wasn't the infinite sum, but the infinite sum would be 0.8. So as n increases, S sub n approaches 0.8. Becomes it, if you will. Now there's a formula used for the actual infinite series sum, which we're about to hit next, I do believe. But that's the final answer there. Okay, so I guess we had to have another graph. Number 20. Excuse me. Find the sum of the infinite geometric series here if it exists. It shall exist because it is geometric and the common ratio is less than 1. I can tell because the numbers are shrinking. They put a plus here. I would much rather put a minus there given that the signs are changing each time. I get it, but I'd rather put a minus there. Okay, so the first term is -2, and the common ratio is, what are we multiplying -2 by to get 1/2, for example? We got to do 1/2 over -2 to figure that out, which is 1/2 times 1 over -2, which is -1/4. Because -1/4, or the absolute value of -1/4 is less than 1, this is a converging series, so we can use the formula. So the infinite sum here is going to take the first term divided by 1 minus r, 1 minus -1/4, which is -2 over 1 plus 1/4, and 1 is also 4/4. 4/4 plus 1/4 is 5/4, so -2 over 5/4, I'm doing this all not in the calculator, is -2 times 4/5, which is -8/5. Here's an exact version of the answer. You can also write -1.6. So that is the converging set there. That is the sum of these all together if this continues infinitely. Number 21 is something that showed up in the section. Write the repeating decimal as a fraction in simplest form. This 0.1212, etc., we can see the repeat of this thing as 0.12. That means this can be rewritten as 0.12 plus 0.0012. plus 0.000012, basically a bunch of 1-2s added together, but in the right spots with zeros afterward. Because this thing is shrinking, it's a geometric series. We have the first term as 0.12 and a common ratio. Let's take 1 divided by, the one before it. And here we'll get 0.01. You're basically dividing by 100 each time, multiplying by 1/100th, so that's the value. And we can use these two things to come up with what this infinite series, what the sum of the infinite series would be, where you take 0.12 over 1 minus 0.01, which is 0.12 over 0.99. Now, you don't want to go to the calculator. They actually want you to have a simplified fraction. They say fraction in simplest form. Multiply both of these by 100, shift the decimal place over, you get 12 over 99. Now, that's not reduced because these can both divide by 3, so you get 4 over 33. So as I was just about to state, every problem in the section that we had would always just be a divided by 99. This is one that actually happens to be able to reduce to something else, which is something I prefer. We didn't actually get any of those before. And very interestingly enough, that if that's the end of the section, first of all, if that's the end of the section, then that means we have 12 questions for 7.5, which is quite a lot. That's crazy. I haven't moved on to the next page yet. And also, we didn't get any diverging series. What you have to note for this problem that we had up here is, and this problem down here, is we got to use this infinite series rule because your common ratio was a number that was less than 1 in its absolute value. 0.01 is less than 1, and negative 1/4. Absolute value of negative 1/4 is also less than 1. These ones check out to use the rule. If this number was 1 or greater, you would not use the rule. You would say there is no sum, the series diverges, blah, 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 because it doesn't add to a finite value. So, do we get to do any problems like that? No. We're going to 7.5 where we have 12 questions to do here. Very interestingly enough, I did not expect that many. All right, section 7.5. I'll just leave these on the screen for now. Before we actually hit them, let's take a look at a couple examples. First example says, write the first 6 terms of the sequence. A sub 0 is 46. And now the 0th term, A sub 0 is your first term. I mentioned that they do that sometimes. That's not common, but they are doing it here. So A sub 0 is your first term. And then for the next term, you take the previous term minus 8. That's how this recursive rule works. First of all, this is the entirety of the recursive rule you have to write, establishing what first term you have and how to get the next successive terms after that. That's how this thing works. Now, they are going to spell this out in a big way that I'm not going to do afterward because they're doing it, because this is the review. But to find the first term, you take, or not the first term, A sub 1, you take A sub 0 minus 8. So 46 minus 8, which is 38. A sub 2 is A sub 1 minus 8, which is 38 minus 8, which is 30. They're basically subtracting 8 each time. So these are the first 6 terms. They didn't write it out as a list, so I'm just going to circle them for you. So 46, then 38, then 30, then 22, then 14, then 6 are the first 6 terms of this apparent arithmetic sequence. And it's arithmetic because it has a common difference. You can see the common difference based on them subtracting 8 each time in this rule. Part B says write a recursive rule for the sequence here. This time we can establish this is your first term, second term, etc. And we're adding 4 each time from one to the next. So they're not talking, by the way, we will hit geometric sequences. We'll hit special cases as well. These are both arithmetic. This one has a common difference of 4. Because of the common difference, you need those two things. You need the first term and common difference, just like you do for explicit rules, the ones we were doing before. So your rule is, starting from the first term of 6, which you have to indicate, you are adding 4 from one term to the next. And that's how this thing appears here. So I'm going to be doing the similar-esque stuff. I'll try and do them pretty quickly. This is running a little over long, I'd say, and we still have 12 more questions to do. The examples took care of them in a nice, slow way, and I think we're allowed to speed them up as a result of that, as long as I leave them on the screen. So, numbers 22 to 24, they're asking you to write the first 6 terms of the sequence. So the first one has a first term of 7. Your next term in the sequence would take the previous term plus 11. Straight up, I'm going to write them out, okay? We start with 7 as the first term. 7 plus 11 is 18. 18 plus 11, etc. This is what we're doing to find all the next terms there. So you're adding 11 from one term to the next. So I'm not going to spell it out too much, especially if this might be the only time I actually get to see an arithmetic sequence After this may be geometric and special case. I don't know, but I can imagine it might be. It is a review after all. Number 23, yes, 23 is a geometric sequence. 24 looks like a special case. Now, number 23, in a geometric sequence, I can tell because we're multiplying from one term to the next. We're starting from 6, and then we multiply the next term, the previous term, by 4 to get the next term. So 6 is the first term, times 4 is 24, times 4, etc. I might have to go to the calculator here in just a moment. Yeah, 396. Yeah, 15, 36. I might have to use a calculator for that one. 36 times 6 is 216 plus 900 is, no, not 900. Oh, I'm not doing times, no, I'm sorry. It was times 4. Times 4. I just said 6 in my head. 600, I'm sorry. 6144. I should use the calculator. Okay. Number 24. Now, this one has a case of f of 0 representing the first term for us. When they say f of 0, it's whatever. It's still our first term. It's our initial. Now, this takes the previous... This is function notation. It doesn't change what we do. Subscript notation, function notation. It still says the next term takes the previous term and does this to it. Now, it says plus 2n. I'm more inclined on this one to actually do work on it. Like, f of 0 was 4. Great. F of 1, this has that 2n. I got to substitute. First of all, I take the previous term, and then I got to substitute 1 into this. Plus 2 times 1 is what's happening here. 4 plus 2 is 6. Does that mean the next one is going to be 8? Not necessarily. No. F of 2 takes the previous term of 6 and does 2 times 2, which is now 10. So, looks like we can tell maybe what we're adding. 2 more than the previous set. Great. But that still works itself out in such a way that you might want to plug these in this way. We need, what, 6 terms? So we're going to go all the way up to f of 5 because we started at f of 0. Okay, so this one is 10 plus 2 times 3. And here's the thing. I can't start out f of 4 until I find out what f of 3 is. F of 3 is going to go into here. Boom. And then plus 2 times 4, which is plus 8, which is 24. And then here we're probably doing plus 10. So 24 plus 2 times 5 is 34. So those are the values. So 4, 6, 10. We don't have to graph these, right? I don't think so. No. Okay, that was the first 3. Let me take a phone call. Give me 1 second. Okay, I'm back, and I think we finished 24. Okay. All right, we're going to go to numbers 25 to 27, where they want you to write a recursive rule for the sequence. Now, we just came off of what recursive rules look like. You need to establish the first term as well as write how the next term is being made. So, in the case of arithmetic sequences, you're going to add from one term to the next or subtract. In a geometric sequence, you're going to multiply from one term to the next, even if it's a fraction, which I believe that's what this one is. And there will be some special case ones that we go, neither arithmetic nor geometric. What's happening? I'm sure we'll recognize what it is when we get there. Okay, so here we go from 9 to 6 to 4. Clearly not arithmetic. It appears very geometric. I believe I can see what it is here. 6 over 9 is 2/3. 4 over 6 is 2/3. You can imagine all the rest. 4 times 2/3 is 8/3, etc. So we do have a common ratio of 2/3, which is important for the rule. Now the first term is 9, but we have to write that with the rule anyway. So I'm just going to write it here. First term is 9. The next term is found by taking 2/3 of the previous value. So that would be the rule that we write here. These will go relatively quickly. Here, by the way. Number 26. 2, 2, 4, 12, 48. Given that the first two are 2 already, it's clear that you are not... This is neither arithmetic nor geometric. It can't be something common, otherwise they would stay as 2s, either adding 0 or multiplying by 1, and that's not this here. Now, let's look into the differences and the ratio. You can either say this is times 1, times 2, times 3, times 4, which appears to be pretty obvious that you're doing that. Or plus 0, plus 2, plus 8, plus 36. I don't see as much of a pattern there. I'm sure there's something you can dig out, but clearly it's that top part that I want to deal with. Times 1, times 2, times 3, times 4. Now, when it comes to writing this, you have to think about how these terms are born. As in, the first term is 2. The second term is taking the previous term 2, let's say a sub 1, is taking your a sub 1 and multiplying by, 1, yes, but recognizing how that 1 fits with the 2 is going to be the important thing, right? A sub 3 takes a sub 2 and multiplies by 2. A sub 4 takes a sub 3 and multiplies by 3. And a sub 5 takes a sub 4 and multiplies by 4. So some a sub n is taking the previous term and multiplying by the quantity that would represent the previous term. That n, but minus 1. So this would be a version that you could write with there. And by the way, a sub 1 was 2. So let me just move that closer to it. Now, you don't need to establish that for the a sub 1 thing because we don't have an a sub 0. You just need to establish what your first term is given what we piece together for the rest of the rule. So that's a good way to building that up, is figuring out where those numbers come into play. If I place an n into here, right, a sub n, well, 4 is n minus 1 and 4 is n minus 1, so it follows up in that light. And that's kind of a special case. That's what we're working out. Number 27. Okay, I already see what number 27's is. We haven't seen it yet in this review. We did do it in previous sets in the section itself. This is not the Fibonacci sequence, but the Fibonacci sequence takes the previous two terms and does something to find the next term. And that's kind of what called attention to me, since the numbers fluctuate a little bit. We go from smaller to bigger to negative to positive. And I decided, well, it's probably based off the last two terms. So take a look at this. 7 and 3. How can you use those to get 4? Oh, 7 minus 3. Can you do 3 minus 4 to get negative 1? Yep. 4 minus negative 1 is 4 plus 1. Is that 5? Yeah, So we're clearly taking this difference of the two previous terms to get the next term. So I don't want to write this out too much, but the third term takes the second, first term minus the second term. First term minus the second term. And the fourth term is the second term minus the third term. And the fifth term is the, I don't want to say third term minus the fourth term. Okay. So with that in mind, the first term is 7. The second term is 2, or 3, excuse me. Second term is 3. We need those two to establish how to get that third term or any term n thereafter. The nth term, we have to take the one that's 2 terms before minus the one that's 1 term before. So like that. You do have to establish not just the first term this time, but also the second term, because the third term is based off those two terms. Number 28 says write a recursive rule for a sub n equals. So this time they have an explicit rule given. It's just a translation from one to the next. This is a geometric sequence. This is a explicit rule for a geometric sequence where the first term straight up is 105 and the common ratio straight up is 3/5. So what do you do for a recursive rule? You write the first term and you state that the next term takes the common ratio times the previous term. And that's it. We're just converting from that to that. And sometimes we did recursive to explicit as well. But there's that straight up conversion. Still 5 more questions. Write an explicit rule. Okay, actually the next ones we are doing exactly what I stated there. We're converting from recursive to explicit. So these would go pretty fast as well, I believe, because generally what you need for explicit rules are spelled out in these recursive rules. You have to come up with what kind of sequence it is. Oh, that's a 26, not a 25. You have to come up with what kind of sequence it is. So this is an arithmetic sequence because you have a common difference. Your first term is -4. Your common difference is 26. We're going to add 26 each time. So your explicit rule takes your first term plus your common difference times n minus 1. That's 26n minus 26, and -4 minus 26 is -30. So this becomes 26n minus 30. Number 30 is a geometric sequence because it shows a common ratio multiplying by -5 each time. So first term is 8. That's needed. Common ratio is -5. That's needed. And again, I want to point out that that's your common ratio. So your a sub n for an explicit rule is your first term times your common ratio to the n minus 1 power. And then number 31 is also a geometric sequence, just with a common ratio that's a fraction. Okay, first term is 26, and it's times 2/5 the n minus 1 power. There, we had a bunch of these. It's no surprise that they gave us 3 of these, because they gave us like 12 of them. Not really, they might have given us 8. They might have given us 12. They gave us a bunch of them in the actual section itself, going like, you know, we did these back in IM1. I don't know, maybe. Oh, I just did number 31. Okay, number 32. A town's population increases at a rate of about 4% per year. So your common ratio is going to be 1.04. If you know anything about this 1, it's to get it to increase every time you multiply by this value. 4% is 0.04. In 2010, the town had a population of 11,120. 2010, they're saying, is going to be your first year. So a sub 1 is not 2010, but 11,120. Write a recursive rule for the population p sub n of the town in year n. So the recursive rule uses the a sub 1 portion. I'm just going to leave it right there. And p sub n, you are going to multiply this by 1.04 each time you increase from the previous year. So I'm not going to use a sub 1, actually. I'm going to say p sub 1. So p sub 1 is 1120, and to get the next set, you got to multiply by 1.04 to make it increase. If it was decreasing, by the way, your common ratio would be 0.96. You'd subtract 0.04 from 1 in a case like that. Is that it? I believe that's it. Okay, number 33, the last question. The numbers 1, 6, 15, and 28 are called hexagonal numbers because they represent the number of dots used to make hexagons. As shown, write a recursive rule for the nth hexagonal number. So the first one we have 1, and then we have 6, and then we have, oh, they have the numbers here, duh. All right, we have 1, 6, 15, and 28, and it continues. They said write a recursive rule in figuring out what you're kind of adding each time, things like that. That might help. Here we're adding 5, and then 9, and then 13. So we're adding 4 more than the previous set. Now, when you do something like this, these recursive rules have an explicit nature into them because their common difference has a common difference, if you will. Where we sometimes have trouble with this. You're starting from 5. In terms of this set that we have right here, imagine that this we had to write a sequence for, the 5, the 9, the 13, where the first term is 5, and then you're adding 4 each time, this n minus 1 times to get from one term to the next. Now, I got to be careful and make sure that I'm doing it right as far as when I go to the second term and such, because I can mess that up. So this might not be proper. Give me one moment on this. This is 5 plus 4n minus 4, which is 4n plus 1. So let's see what happens if I'm doing that right. To go to the second term, see I have this a little bit off. To go to the second term, I'm adding 5. I'm not adding 4 times 2 plus 1. I'm not adding 9. So I actually have to go a little bit less than this. I just have to make sure how to establish that for you guys, because it's not 5 plus 4n minus 1. It's actually 1 plus 4n minus 1. I think maybe I'm supposed to use that number. No, 1 before it. I guess 1 plus 4n minus 1. So it's 4n minus 3 in this case. I got to get better at that and explaining it. There's some way to do it. But basically, now when I substitute 2, here's how this works. When it comes to your rule, your first term is 1. And then your next term takes your previous term, and it adds, we're adding basically this a sub n. Not a sub n as in this a sub n. Oh, shoot, I shouldn't be using this letter. We're adding 4n minus 3. I'm having trouble explaining this one. We're adding 4n minus 3. To show you how this thing works, for the second term, we take the first term's value and we're adding 4 times 2 minus 3. Now the first term is 1. 4 times 2 minus 3 is 5. That's where we get the 6. The third term takes the second term plus 4 times 3 minus 3. It's 4 more than the previous thing. So that's 6 plus 12 minus 3, which is 9, which equals 15. So this does work itself out the way that we want to. Let's do the last one. A sub 4 takes the third term plus 4 times 4 minus 3, which is 15, plus 16 minus 3 is 13, which is 28. So it is working out. This is the answer. What I have to get better at is the explanation as to either why this starts with 1 or how you determine, what this minus 3 begins with instead of the plus 1. That's the one part I kind of messed up on when writing these things. I think you had to establish that this would have been a plus 1 to get to the first term. And then maybe you can now tell that that's a 1 that goes there. That number had to be used there. And I think that's one part that I just missed a little bit. Otherwise, that's the answer. That's what we get. We're all good. Guys, that'll do it for this one. This is Mr. Robinson. Thank you so much for watching the Chapter 7 review. Now, when we hit the Chapter 7 test and cumulative assessment, I say this each time, and I'll say it again, I'm going to be going a lot faster with them. Probably no real teaching and a lot more doing unless it's a brand new type of problem or a problem stumps me a little bit. They're bound to happen. This one, I would state this a lot faster given what we were doing, even on that last number 33 question as well. And just like, I'm going at it, here's what we get. Because now you're testing your knowledge against what we've been learning the entire chapter. Thank you guys so much. Take care. I'm going to see you in that next one.